Welcome everyone. I recently found a problem from the problem solving section of chapter 6 of Stewart's calculus, and today I just want to share my solution to it because I think it's really fun. We're given a semicircle with a radius of 1 and a line parallel to the diameter of the semicircle. This line has some height h above the diameter, and this h, the value of it can range anywhere between 0 and 1. So the problem is to minimize the area shaded in here. And what is shaded in here? Well, first above the line and within the circle is this area, and also below the line and outside the circle, and also bound by these two vertical lines, which are tangent to the ends of this arc. And as I said, the problem is to minimize this area. So we have to find such a height of this line such that the area is the smallest possible. Let's get right into it. Let me outline the approach I'll be using in solving this problem. It really is quite straightforward and can be broken down into 3 steps. So our first step is to define such a function of h that measures the desired area. So we'll call that function a of h, a for area, which measures what is shaded in right here. That's our first step. Our second step is to take the first derivative of this function and then solve for the equation a prime of h equals to 0. We'll get our critical points of the function then, where the function does not change, and then we can justify whether it is a minimum or not. And that is our third step, to justify. And that's basically going to be the method here. So let us get right into finding this function, a of h. How do we define it? I think the best way to find this shaded area is to use integration. And to use integration, we have to first define our curve. And we can either do that explicitly or through parameters. So let's take a look at our options real quick here. We have to define our semicircle as a curve, and we can do that either as a relation y equals the square root of 1 minus x squared, just a function of x, or we can use parameters, so x will be equal to the cosine of theta, and y will be equal to the sine of theta, right? All makes sense, as theta ranges from 0 all the way to pi. So the full circle doesn't go to pi over 2, but goes to pi, like this. In doing this, we also have to call the origin the center of our semicircle. So let this point right here be 0, 0, the origin, and it may be also helpful to draw a little y-axis right here. So this is y, and this is x. Now, there actually turn out to be a handful of ways in which we can describe this area through an integral. We can either use this function and integrate with respect to x, we can use this function and integrate with respect to y, or we can use the parameters and integrate with respect to x or y. But my favorite method is going to be using the parameters and integrating with respect to y, because everything turned out to be quite simple and there's not much algebra involved. But all the other methods are equivalent as shown on screen. If you don't remember how parametric integration works, I reminded you of the theorem right here. It's basically just a u substitution, but with the parameters. But anyways, let me show you how we're going to find this shaded area. We're going to, of course, use these parameters. And let me quickly make a sketch of the angle right here to make it make more sense. So here we have our theta right here, which is our parameter, and it's making this right triangle. My goal right now is to find the area bound by the y-axis and this curve, so this little part right here. And to do that parametrically, we have to know the values of theta at each of the ends. So right here at this end, we know, of course, that the sine of theta is equal to h, and therefore theta is equal to the inverse sine of h, or the arc sine. And right here, where the curve meets the y-axis, we know that theta equals to pi over 2. And right here, as I said, it's equal to the inverse sine of h. And so to find this little area, we simply have to integrate parametrically by this theorem through these bounds. I'm going to call this entire top area a of u because it's the upper area, and it's going to equal twice of this integral that I just described, right? Because there's one half and then there's the other half. And this integral is going to be from the inverse sine of h to pi over 2, and then by the parametric integration theorem, we just simply substitute in x, so cosine of theta, and then times the derivative of sine, which is cosine, so cosine squared of theta in d theta. And this is going to be our upper area. Now let's do the lower one. Now for the area of the sides, which I will call a of s, it's really quite a similar process with the integration, but there's now some subtraction involved. So notice this area is simply equal to the value of this rectangular box minus this area bound by the y-axis and what's inside this circle. But isn't that what we just did by the y-axis and inside the circle, simply like this through the bounds of theta? So we can do just that. We can multiply everything by 2 because it's going to be twice of what we're doing. And first we're going to take the value, the area of this rectangle. It's going to be 1 times h. So h. And then we're going to subtract the integral from theta equals 0 all the way to the arcsine of h into here. You see, this area bound by the y-axis and what's inside this curve is going to be the integral from 0 to the arcsine of h, and then by the same function, the cosine squared of theta in d theta. And these are going to be our two components of area, and then we have basically defined our area function. We're just going to sum these two up, and there already is the h variable in here. So that is all done. All right, so we have our area function, and it looks like this. Not the friendliest, right? But remember, our goal is to take its derivative, and there are a bunch of integrals here. So by the fundamental theorem of calculus, the differentiation and integration should cancel each other out. That is precisely what happens. You could also do it the boring way and just evaluate these integrals here, but that's not too cool. So let us do it that way. But to do that, we'll have to get a single parameter in here, not some function of h. We'll have to get a single variable into these integrals. So we can simply do that by substitution. Let us have some new variable, t, equal to the arcsine of h. Let t equal to arcsine of h. Now we can write a function equivalent to a of h. Let's call it g. We can get that g of t is equal to a of h, which is going to equal simply swapping this inverse sine of h for t. Going to be 2 times, and also here I'm going to swap the bounds of integration just to make the fundamental theorem more clearer. The negative integral from pi over 2 to t of whatever cosine squared of theta, then minus again the integral from 0 to t of cosine squared of theta, and then plus h, and h is equal to the sine of t, like this. The whole point of writing this as a new function g is so that now we can differentiate with respect to t of this function g. So d over dt of g of t, and if we convert it to a of h terms, it's going to be slightly weird. We're going to be taking the derivative with respect to t of a function of h, but don't worry, we will clean that up very soon. But really, now we can take this derivative and all of these integrals will simply vanish by the fundamental theorem of calculus, yielding us a result of simply negative 2 cosine squared of t, and then here it seems like the same thing, negative 2 cosine squared of t, and here it's going to be 2 times sine of t. The derivative of 2 times sine of t is 2 times cosine of t, and so we get that our derivative of the function g with respect to t is this right here. This is going to be cleaned up a bit. It's going to be negative 4 cosine squared of t, then plus 2 cosine of t, which is just equal to cosine of t, and then times negative 4 cosine of t, and then plus 2. All right. Now we have a derivative for g, but not for a of h. So now we have to address this part, d over dt of a of h. Let us keep going in this chain of equal signs. We know that d of a of h is simply a prime of h times dh, and then this is all divided by dt, right? Now dh, we know that h is equal to the sine of t from this relation. So d of h is simply equal to cosine t of dt. Don't you see it? So this is equal to a prime h, d of h is sine of t. The difference of it is the cosine of t. So this is going to be cosine of t times dt. And then all over dt, look at that, these t's cancel out. Therefore, d over dt of g of t equals to the derivative of a with respect to h, a prime of h, times cosine of t. And look at that, cosine t over here and over here, and therefore a prime of h, the derivative of a with respect to h, is equal to this part right here, negative 4 cosine of t, and then plus 2. All right, so now we have the derivative of our area function. Now we have to simply set it equal to 0 and find these solutions. But not all of the solutions, only the solutions valid on a domain. Remember, this has infinitely many solutions when it's set equal to 0. But remember, the domain of our h is from 0 to 1 inclusive. And we know that t is equal to the inverse sine of h. So we can find the domain for t. We know that this now implies that t is on the interval of what? So when h is 0, t is equal to the arcsine of 0, it's also 0. And when h is 1, t is equal to the arcsine of 1, which is pi over 2. So t is simply on the interval from 0 to pi over 2. All right, so we're looking for solutions to this equation on that interval. Let's try it. If we set this derivative equal to 0, then we can simply move this over, divide by 2, get that cosine of t is equal to 1/2. And there is only one solution on this domain, and that is when t is equal to pi over 3. So we get that as our answer for t. And therefore h we get is equal to the sine of pi over 3, or root 3 over 2. H is equal to root 3 over 2. Great, so now we solved this equation, but now we have to do our third part. Now to verify that this value of t or of h is in fact the minimum, we can do one of two things. One, we can simply look at the graph of the area function. When I say simply, it's not that simple. It may be really hard to graph this function without a graphing calculator, but if you have the tool, you might as well use it. But the second option is the very reliable second derivative test. And if we do that, we get that it is, of course, negative at this value of h. Therefore, it is, in fact, a minimum. And therefore, we know that this value of h is the height of such a line that, when cut through the circle, will minimize the shaded area. And just for fun, if you want to compute it, if you want to compute a of the square root of 3 over 2, so evaluate these two integrals. I won't do it right here, the computation, you can try it yourself. You will get a very nice value of square root of 3 over 2 minus pi over 6, which is about 0.34. So that is really it for today's problem. Thank you all so much for watching, and I will see you next week.